So coming off of what we were talking about today in class with developing this concept of Q and what we're going to be doing in lab on Thursday, I want to start to talk about this concept of Le Chatelier's principle. And Le Chatelier's principle states that if a system at equilibrium is disturbed, the system responds by undoing, at least partially, what has just been done. Let me write that down. So there are two ways in which this can actually happen. The first is that you have the reaction move to the right or towards the products. And of course the other is moving to the left or towards the reactants. Now this may all sound a little bit confusing, but in reality it makes a lot of sense as to what would be going on here. And I think what's important here is to look at this from the perspective of the seesaw. Okay? Imagine that you have to have a situation where the seesaw always stays in balance. So if I were to put a weight on this side, it would obviously drag it down in this direction. And in order to make sure that I go back to equilibrium, I would need to make sure that I put an equal weight over on this side. Or I could actually shift whatever was happening on the, in this case, left side and move it over towards the right side. So it would be not necessarily moving this pink thing as I'm doing it, like so, but it might be changing the pink thing into something that's a blue color, let's say. Let me erase this little pink bit here, so that that blue thing ends up over on this side to balance it all out. Now, of course, when that happens, you're going to have it move down in this direction, and so you have to make sure that once you disrupt the system, it's going to have to come to some level of equilibrium where you have something, in a sense, half pink and half blue in the middle. And when that's the case, then you've met that equilibrium point once again. So let's take a look at this with an example. New page. All right, the family is done eating, so I'm going to pick this up in just a moment. Okay, so I'm back at home now and I have my regular mic, so I hope this is coming through a little bit more clearly. So what we're going to be looking at here is a reaction where we take nitrogen gas and hydrogen gas to form ammonia. And it is a reversible reaction. And I want you to imagine I decide to introduce this as a perturbation or as something disturbing the equilibrium of the system. So if I decide to increase the concentration of the N2 in order to come back to equilibrium, we're going to have to make sure that this whole system shifts in the direction of the products, going in this direction. Because in that case, you're going to have a Q, if I increase the concentration of the N2, which is going to be less than the KEQ. All right, the Q is less than the KEQ. And don't forget, in order to understand that, the reactants are part of the denominator of the reaction. So if the denominator becomes bigger, it makes the Q smaller relative to the KEQ. And when that's the case, we're going to shift to the right. All right, so imagine this situation. Instead, I decide that I'm going to increase the concentration of the ammonia in this situation. So I add in extra ammonia. And when that happens, I think if you were to slow down and think about this, then we have the opposite occurring, where we have the Q, which is greater than the KEQ, because we have a larger numerator relative to the denominator. And when that happens, we have a shift to the left. Okay, so just be sure that you're getting this, that if you push on one side of the system in order to counteract that, you have to make sure you move it towards the other side of the system to counterbalance it like a teeter-totter. Now similarly, what if I decide that instead of increasing concentrations, I'm going to decrease the concentration? And in this case, I'm going to decrease the concentration of the nitrogen gas. And when this is the case, we're going to have a Q, which is going to be greater than the KEQ. And when this happens, the same thing will happen as just above it. We're going to have another shift to the left. And similarly, if I decide that I'm going to lower the ammonium, in order to counterbalance this thing, if I remove a little bit of this stuff, then it's going to want to shift back in that direction. And I'm going to have a Q, which is less than the KEQ, and as a result of that, it's going to shift to the right. All right, you might want to go back over and think about each one of those scenarios in order to understand what's going on here. And it's all governed by this concept of Le Chatelier's rule or principle, which says that if something is in equilibrium and it's disturbed, the system will respond by undoing what has just been done. So that's if we have a change in concentration, focusing on a change in concentration in all those cases. What if we instead have a change in temperature? I'm going to go to a new thing for this one. And if we're going to do change in temperature, let's go back to our old friend, the smog making. So there's our reaction, and I'm going to add one more thing to this, which is that this is an exothermic reaction. And if it's an exothermic reaction, I could either show it as a delta H equals a negative 57.2 kilojoules, okay? Or don't forget, you can actually include the energy either in the reactant side or the product side, depending on what kind of reaction this is. And if it's an exothermic reaction, then we want to add the energy to the product side. So I'm just going to erase this, and instead of having it off to the side like that, I'm going to include it, in a sense, as one of my products, because energy is given off, and so in a sense you can think of that as being a product in an exothermic reaction. So if we do have the energy as a product in this case, I want you to think of what would happen if we change the temperature. So imagine this where I add heat to the whole system. Okay, so both sides essentially get heat, both the reactants and product sides get heat. But if you're adding it to the whole system, then it's in a sense it's going to affect one side more than the other. Think of heat in this case as being a product. So if you were to think of this in the concentration piece that we did earlier right here, you had no problem understanding that if I were to, I didn't close off the bracket there, if I were to increase the amount of ammonium on the product side, it would make the whole thing shift towards the reactants. Well, if I add heat to this whole system, and that means it's going to be an additional, in this case, it's going to be this as the product. It's like increasing the concentration of this thing. So when I add heat, that means it's going to be pushing it back towards this direction, right? To counteract that through Le Chatelier. And then obviously you could imagine doing just the opposite. If instead I withdraw heat or I cool the system, in a sense what that's doing is it's taking away, it's like lowering the concentration of the product on this side. And so if that's the case, because it's an exothermic system, it's going to make the reaction shift to the right. Okay, so again, you might need to sort of sit back for a moment and think about that before you move on. It's always nice to sort of memorize these things, but you have to be careful. It's always better to really understand fundamentally what's happening before you just commit it to memory, because you never know, I might get tricky on you. Now, here's the thing that's kind of cool about this. This actually explains a lot why smog is more of an issue in LA than, say, Boston. I mean, there's other contributing factors too, like LA is surrounded by mountains, so it's really hard for any sort of air mass to get out of there, whereas Boston is not. But in LA, it's much hotter, right? And because it's always traditionally much hotter in LA than it is, say, in Boston, that means we're adding heat to this reaction. And as a result of adding heat to this reaction, it has no choice but to move in this direction, back towards the smog, right? Oh, whoa, what happened there? All right, so this is the smog. And that's why it's one of the reasons why LA has much more of a smog issue than Boston does. Now, I hope you understand that if this were an endothermic reaction, we'd have to reverse everything. So let me just quickly throw an endothermic reaction up here just so you can be sure you understand it. If you think you get this, then you can probably pass through this pretty quickly, but it's not a bad idea to see this as an example. Okay, in this example, I have an ionic solid the barium chlorate, and it dissolves in water. And it doesn't dissolve very well in water. You should understand that. It's only slightly soluble. So it dissolves a little bit, but then it will reform back into the solid precipitate, and then it'll dissolve a little bit more. So this is a perfect example of a reversible reaction. So it's a little strange to think of solubility and reversible reactions, but it works just the same. And in this case, this is an endothermic reaction. So again, I could choose to write the delta H off to the side as a positive 28.0 kilojoules, or I could decide to actually incorporate it into this reaction. So instead of doing that, I'm going to go ahead and incorporate it. So I'm going to take this positive 28, and since it's an endothermic reaction, in a sense, it is something that becomes one of the reactants. So I'm just going to write 28 kilojoules over here on our reactant side of things. Sorry, I should have planned better here. You can't see the whole thing. So in this case, if I were to increase the temperature, it would be as if I were increasing the concentration of the energy on this side. So I think you can understand then that if I increase the temperature, this reaction is going to move towards the products or towards the right. And conversely, if I were to cool this, it would be like I was removing some of this heat, and as a result of that, in order to counteract that, it would move back to the left. And again, this only applies to a reaction, an endothermic reaction. All right, last thing. So what happens if we change the pressure? So we looked at changing the concentration, then we looked at changing the temperature. Now let's look at changing the pressure. You're probably sick of seeing this reversible reaction, but it really happens to work really quite nicely when we're talking about change in pressure. What? Are you okay, Mommy? And if we have a situation where we want to look at pressure, we should know that there's a nice little rule of thumb to use here. Here it is. If you increase the pressure of a system, it will shift the reaction towards a decrease in pressure. That may seem a little bit baffling here, but imagine that you had this reaction here and it was in a closed container. Okay, so it had a fixed volume, and we just had both a combination of NO2 and N2O4 in a fixed container. Now, if I were to increase the pressure somehow within this sealed container, I think you can see here, and don't forget, this is an important thing, these gases right here take up as much space. So if we go back to way back to the fall term, 1 mole of a gas is 22.4 liters of that gas. It doesn't make a difference what the gas is, and these are both gases. It's still going to be occupy 22.4 liters. And again, the reason for that is that there's so much space that exists around gas particles. So the size of the particle itself doesn't really make much of a difference. So in this case, we should understand if 22.4 liters at STP would be 1 mole, that is what I have here. So if we were to do this at STP and I had a liter of it, then I'd have 1 mole of a gas at 22.4 liters if that gas were the N2O4. And in that same situation, you can see here that I have 2 moles of the NO2. So if I were to increase the pressure, in order to make the pressure decrease, it would be better to have this whole reaction move in this direction, because then you would lower the number of lower the number of moles of gas. And if you lower the number of moles of gas, then you're going to decrease the pressure of that gas. This goes back to talking about gas laws that we covered in the winter term, right? I think you all understand that Avogadro's law there. All right, so in order to sort of summarize this, if we increase the pressure, at least of this system that we have right here, given that we have 2 moles of something and then 1 mole of something, if we increase the pressure, then it's going to shift in this direction towards the N2O4, whereas if we decrease the pressure, it'll do just the opposite. Think of pressure in a sense as being a reactant in this reaction, and so as a result of losing some of that reactant, it's going to move backwards towards the NO2. Now, I want you to very importantly notice that we're talking about gases here. We're not talking about liquids and solids here. So pressure only comes into play when we're talking about gases, and this would be a homogeneous reaction, I think you can see. All right, crew, that's enough. I'll see you on Thursday.